Hey, John here. I'm working on some Verilog example programs. Today, let's talk about how to install the toolchain we need to compile these and run them on the Lattice Ice Series chips, specifically on the UPduino and or the Icestick board. Now, I've also got a board that I've been working on myself, which is this Project 2057 over here, and I've got a configuration for that board as well. That has an HX4K chip in it and the TQ144 pinout. So we have three different boards that the same set of code here can be targeting. It can also be built to run in simulation. If you scroll down on this page, you can see the GUI that pops up. We can look at these waveforms of the FPGA running the code, what's happening inside the chip. So let's go over how to install these tools so that we can all use them. Now, I've run this on Ubuntu 22.04 and Ubuntu 20.04. I've also got another variation of this ported over and running on a Raspberry Pi. That needs a little bit more work. I'll get there at some other time. For now, let's just look at Ubuntu 20 and 22, okay? So, if you're on Ubuntu 22, it's real easy. You just run these commands, you're done. You have all the tools. If you're on Ubuntu 20 or something like a Raspberry Pi, then you got a little more work to do. You can get the iVerilog and the GTK Wave. You then have to install the various compilers and dependencies and things like that. Then down here, you can download from the Git repos the actual source code to these tools, the Icestorm, NextPNR, and Yosis. Up here, if you look, what happens is this grabs Icestorm and it grabs Yosis in one package. NextPNR comes in down here, okay? So if you go ahead and do the compile and build route, what happens is the make install will put all the files underneath user local. Now, normally user local should be in your path by default, so this is not a bad place for it to go. And there's usually nothing down there already if you're on a relatively clean distribution of your OS. They start them out empty. It's really so that you can do things like this and install apps on your own. So, pick one of these. Let me know if it works or not. Comments below. If I made a mistake in here or there's a better way to do this, please let me know. It took me a long time to work this out when I first did it the first time. These days, it's pretty nice. 4 or 5 years ago, it was a little more complicated. Okay, so you can either install it direct if your OS distribution supports it, or you can build it as shown above. Now, what do we got here? We have to configure your FPGA board. We have to clone this repo in the usual way, right? Come in here, click this. You can either use HTTPS or SSH. I use SSH. The result is you go down to your machine and you type git clone, whatever. And then you use whatever method you want. You copy this. Then you paste it into your window. And that gives you your repo. So here's Verilog examples. You get rid of the .git. You see what's in there, the usual stuff, some makefiles and some other things. Now this is set up so that you can use the top level makefile by default to compile for the UPduino, as I talk about in the README file below here. All right, so underneath is this configuring of your board. Let's get a bigger font here. I love it the way that by default they waste this whole side over here. It's kind of annoying, but whatever. It makes some weird sense. If you click directly on the README, then we get a closer view. Sorry about that. Okay, so how do we configure your board? By default, it's configured for the UP here. That is a UP5K FPGA on it. If you want to use an Icestick instead, you want to create a makefile local in the top of the repo, and we'll do this in a minute because I got an Icestick as well. And then you're configured for the Icestick instead. Or if you're using the 2057 board, you put this in makefile local. Or you can, by default, it's already going to use the UPduino, but you can explicitly make the UPduino be the target board by putting that in a makefile local. All right. So I just cloned it, so I don't have a make local. as you can see, all right? There's all these rules. These are the files that get included in this make local files. You can see the UPduino or the whatever, the 2057 and so on. All right, so these I already give you, and these are already all set up. Let's look at what's going on in one of these, just so you know. In order to compile and program your board, the build environment needs to know, how do I run the programming command? Where are the pins on the FPGA? Because they're all different, right? What kind of a package is it in? What kind of a FPGA is it? That sort of thing. All right. So the comment right here is wrong. I will fix that right now. For the UPduino board. Yeah, always good to have nice incorrect comments. Sorry about that. Okay, so here we go. All right. So by default, it's set up for UPduino. Now, I have one on my bench, and I've got a couple of different programs right here. Let's go for the gold and run Blinky 2. What that's going to do is it's going to just make the LED on the UPduino. It comes with like an RGB LED. It's just got one, but you can change colors and stuff like that. So if I compile this, now, if you've ever used something like the Xilinx ISE, you might be amazed at how fast this goes. I was the first time I used it. I said, surely that can't work. I'm used to the 2 and 5 minute compiles. Granted, this is a very simple build, but yeah, I'm just saying. So you type make to compile it, you type make prog to program it, and you're in business. Just gonna type in my password. 10% more likely to work when it's plugged in. And there we go. It downloads it. It's going to put it in a flash ROM, and it boots up. And of course, the LED is so bright, it blinds my corneas. So I'll put something on top of there like this so that I don't have to stare at it. All right, so let's say we don't have a UPduino, and instead we want to use the Icestick, right? So you go back to the site here, and it says, how do I configure for the Icestick, right? You say, it says create a file called make file local, and then put this in there. So I make, oops, I'm in the wrong, yeah, I'm back up at the top here, right? Oops, make.local, and put that line in there. Okay. Now I'm going to just type make cleanup at the top to delete all the files, because if you ever change your target, you're going to have to forcibly recompile everything. Otherwise, you could be doing something like downloading an HX configuration file for a UP chip or something weird like that, right? So I wouldn't expect you to have to change this very often. You'd probably just do it once, leave it alone for whatever board you're using, okay? But I have 2 boards, and I want to try them on both today. Let's go back to Blinky 2 here. Now, remember, I typed make clean, so all the files and stuff are gone. So first we have to get the other board plugged in. So this is my Icestick, out with the UP, in with the HX board. Plug that into my PC. Then type make. You can just type make prog if you want. It'll do the full build and everything, and then it'll download it to the chip. And you can see the variation here, because this does not have an RGB LED. It has discrete LEDs. And the program really turns on and off the red, green, and blue LEDs independently on the UPduino, while this one, it's turning on discrete LEDs one at a time. That's what you need to know to program Blinky 2. There's also a Blinky and a Minimal. You can play with all 3 of these apps. They should all work on both of those boards using the technique I just showed you. If you really want to use the UPduino and make it explicit, you can put that in your make local as well. Oops. Let's just put both in here and comment one of them out. That seems more reasonable, right? That way I can switch them back and forth, okay? Now I'm switched back to the the 5K board, right? So that's for programming and for configuring. Let's talk now about simulation. Let's go back to Blinky 2. Now, the truth be told, it's really neat to be able to blink lights and stuff. And I insist that I get there as quickly as possible when I start a new project, in order to verify that the tool chain works, the installation worked, all this other garbage that takes like thousands of hours, all so you can sit down and write your nice little app that you believe you'll finish in 5 minutes. But when reality sets in, it'll be days and days and days, and if not months, before that gets done. And when you're working on these programs, my point is you're going to spend a lot more time simulating things than you are running them on your hardware, certainly when you're doing your development. And this is like very much so when it comes to writing code in HDLs like Verilog, because you can't put probes and stuff inside the FPGA. I mean, they have, they have various things that you can use to connect up to FPGAs, and you know, they can sort of extract signals out of them, and they've got some nice tooling for that and all, but just about nobody really expects to work that way when you're doing real development, okay? What you usually do is you create what's called a test bench, and you write explicit tests for these things. You don't even need the hardware to do this, okay? So I'm going to type make clean, and all the files get cleaned up that were generated to be programmed. Now, instead of make program, you can type make, I'm going to say make minus n plot. Let's look and see what this thing actually does. What it's going to do, make minus n, I like to think of this as not really, okay? It's going to go through the motions that it needs to make a file, but it's not really going to do it. It's going to say, if you really asked me to do this, I would run that command, then I would run this command, then I'm going to do this. So this lets us see what we're going to do before we actually do it. So what is it going to do? It's going to run a compiler of some kind, then it's going to run a thing that's going to simulate what an FPGA will do using this so-called test bench program. We'll talk about that some other time. That's a subject of a whole sit-down of its own. Okay? Then it's going to run a program called GTK Wave, which is a graphic application. It's going to pop open a GUI and let us see these little waveform diagrams. Now, hopefully I logged in so we can see that thing open up. All right, so when I ran it, it popped this up. Okay? It actually went through, as you can see, the motions. It compiled it, and it created this thing called a dump file and so on. And this is, I don't know why that keeps coming up. That's just some stupid, silly warning that comes up on almost every app I ever run, which has to do with the graphic toolkit that is being used. And then it talks about start times and end times, and it gives you a chart that looks like this. Okay? Now, if you click this and open this tree up, see where it says UUT? As we'll see when we actually write one of these things, this is called unit under test. That's a name that I gave a module inside the code. So I'm the one who created these names. These are names of variables and stuff. So when I created a program in Verilog, that program has various variables in it. The data types are wire and register. And we'll see all about this at some other time as well. But the bottom line is you can simulate what the FPGA is doing, and then you can see what's going on. So in here you can, if I hold down the control key and click on various rows in here, or if I click down here and then click on control A or something like that, it'll select all of them. And then if you click append, it'll put them all over here. And while I was talking, I double-clicked over here, which is another way to copy these variables onto this timeline over here. If you click this magnifying glass over here with a check mark in it, or sometimes it's got a little square box in there or whatever, click around some of these icons. One of them is zoom to fit, okay? Now what this has just done, and we'll have to look at the program at some point to understand more about what's really going on here, but this is just about running these tools and make sure that you have an environment that you can run these programs in, so when we do talk about them, you can follow along on your own system here, okay? Now, what this thing is doing when it flashes the LEDs, as you may recall, some of them are flashing faster than other ones. And the way I made that work is I simply created a counter, and you can even see that variable right there. It's called counter. This is a 32-bit counter. What I'm doing is counting at millions of times a second, multiple megahertz, and I'm showing some of the bits of this counter on the LEDs. Now, one of my other boards, the 2057 board, has 8 LEDs on it, so I wrote this program with 8 output bits. And on the Icestick, there's only 5. On the UPduino, there's really only 3 when it does its colors. So what happens, and again, this is subject for another time, the extra bits, when I configure the board, I just throw them away by connecting them up to, pins, GPIO pins and stuff on the board that are otherwise not used. Okay, just to satisfy the needs of the tool. Again, we'll talk about the details of that some other time. High-level view, though, there's a clock that's running at multiple millions of times a second. There's a counter that counts up by 1 every time the clock ticks. And I look at 8 of the 32 bits, the most significant bits probably, by sending them out to the LED control lines, all right? There's also a reset pin in there. Neither of these boards that I just showed you has any push buttons on it, but the 2057 board does, and I have a push button hooked up to a reset that can be used to reset the count. So that's what the application does in general. And as I play around with this tool, if I hold down the control key and I move the mouse wheel, that's what I'm doing here for zooming in and out, all right? These other things, if I click with my left mouse button, it puts this red line on there. If I click the mouse wheel or the middle button, it puts a white line on there. And you can see what's happening up here as you move these things around. If you click the mouse wheel twice, it goes on and then it goes back off, okay? And the red line is with the left mouse button. And these two have different purposes. This is called, obviously, the marker. If I click it somewhere, it tells me what is the time on this time scale up here. That's represented by where that marker is right now. I can also click here and then drag the marker, and you can see it says plus 1150 nanoseconds. So that's the distance between these two markers right here. If I release the mouse, the other one disappears and then, it moves over here. So get used to how this tool works and zooming in and out. If I, again, put down the control key and mouse forward, I'm zooming in here. So what I'm seeing in here is the value of my binary counter while it's running. Okay? This is your, if you want to go back to the beginning, you can do this sort of thing. And if you're fortunate enough to have enough stuff going on over here, there's a vertical scroll bar as well. So you can get an awful lot going on in a real big project you usually do. Now, in this simulation, because this doesn't involve any hardware at all, it's purely software. Again, we'll talk about it some other time. What I did is I told the simulation to simulate the clock ticking every 100 nanoseconds. So this is what? 5 megahertz, if you think about this in terms of a clock period, right? And every time the clock ticks, you can see the counter goes up by 1. Ticks again, it's at 2, click again, it goes up to 3, 4, 5, and so on. The LEDs here, at the moment, they're all set to 0. And reset is you see this line in the middle here that says that it doesn't have a value. It is an invalid. It's floating. It's not specified. And we'll talk about more of this stuff later. All this will make a lot more sense if we actually look at the program that we're trying to run here, simulate here, and trying to debug. Why is this 0? How come reset doesn't have a valid value and it's floating right now? Okay? These are features that'll make more sense when we have time to sit down and really go through the code. For now, this is about making sure you got the tools installed, make sure you can run them, make sure that if you have an Icestick or a UPduino that you can actually program it and see the lights flashing and stuff like that. All right? Now, there is a data point that suddenly comes to mind. I'm going to have to add a link to this page here, specifically about the UPduino. And that is that this chip, not the chip, but the board, the UPduino board, has a feature about it that is discussed right here. Okay, I'll put a link in the README file. In fact, I can do that right now. Why don't I edit this so I don't forget? Blah, 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 yada, yada. Configure your board by default. This does this, yada, yada, yada. If you're using these other ones, do this other stuff. I will paste that URL in right there to remind me I need to take care of that. Now, back to the details. I will link to this page, okay, so you can find it. What happens is, as it states here, the UPduino has an onboard oscillator that does 12 megahertz clock. And you can use that if you connect it to this pin here in the FPGA, so that you can use the oscillator ticking to do what you just saw in the simulator I had running at 5 megahertz. This one would be running at 12 megahertz. But when you buy your UPduino, it's not connected. So if you were to run my program on a UPduino, it'll just sit there. It'll never change colors because the clock is not ticking. They give you a little view of the schematic here, and they say that this R16 jumper is not installed when you get your UPduino, okay? If you want to install it, you can do a couple of things. You can solder a little blob of solder, a teeny little wire on this little jumper spot on your board, which they show down here, okay? It's this little thing that looks like this. Or what you can do is you can take a wire and connect from this pin here over to that one there on your board itself, which I believe you do by running a wire from, this is actually an incorrect silk screen, I believe. Find the pin that says 12 megahertz on it and connect it over to this pin here that says 20. Because this goes to pin 20. The way they wrote this, the way they drew this up, I'm not happy with this. They should have shown the fact that this goes over here, that on this pin over here on your UPduino board. That way it would be much easier for you to understand. If you solder in the headers on your UPduino and you stick it in a breadboard, you can put a little jumper and connect the 12 megahertz line to pin IO pin number 20 over here. Now, you can also find out with FPGAs, you notice it doesn't say 20, 21, 22, and so on. These are the names of the signals from the perspective of the CPU. All right? There's another page in this website. Where is it over here? Yeah, under errata. And on this page, what does it talk about? A couple of things. GPIO 20 is used for the onboard 12 megahertz clock oscillator if the jumper is shorted. But if it's not, which is what it is when you buy it, you don't have access to this oscillator. And my program, is my point, won't run on your UPduino. Now, I installed it on my board, but honestly, it was a little fiddly. If you're not happy with soldering tiny little parts, you probably don't want to do that. Instead, what you should do is connect your GPIO 20 to the 12 megahertz oscillator in your breadboard by putting a jumper, and this is what I was trying to show you in the other diagram, between this 12 megahertz line and this GPIO 20 line right here. All right. It also talks below here that the ground and the 12 megahertz pins were backwards in an earlier version of the UPduino. Mine happens to be a 3.1, which does match this diagram here. But you can see it's a 20, a 10, a ground, and a 12 megahertz right there. If we back up to the page that we were on before, you'll notice it goes 20, 10, 12 megahertz. This is actually a picture of the UPduino 3.0, which has the wrong silk screen on it. Okay? Now, In their defense, they're talking about, in this context, putting a little jumper here, soldering a little wire onto this little pad right there. But when I was doing mine, I noticed that it's really close to this part right here. And if you're, if you're not super careful with your soldering iron, you could start unsoldering this part here or the one up there. Then you got a problem. Okay. So my point, what I'm trying to make here is, if you put a jumper from the pin on your UPduino that says 20 and run it over to 12 megahertz, which, as I talked about before, note that it's wrong if you have a 3.0. The silkscreen on the board is correct if you have a 3.1, because that's what I have, and I checked, and yes, it is correct. So be careful what you're looking at in this site here, and here it shows one thing, another one that says this is wrong, blah, 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 blah. Be careful, all right? So, in my opinion, what you want to do is connect this thing here over to that there. This is on pin 20. This is like 3 pins to the left, all right? Which is the one right over here, okay? So if you do that, then the light will flash colors. If you're on my program without that jumper in there, it'll just stay on one color and never really change. This should be enough to get you plenty dangerous. Let's go ahead and look at some of the code here. Let's do a quick make clean and see what's going on. If you want to read ahead, there's a top.v that stands for Verilog, okay? And there's a counter TB. This is the test bench program that I use to generate the fake signals and stuff for the plotting. And counter is the thing that actually runs the application itself. If you look in these files, none of them are particularly big. These are really simple little programs. You'll notice that there's a module in each one. A module is a piece of hardware in terms of the VHDL concept. In my mind, they also feel a lot like subroutines. If it was really just software, these modules would be subroutines or functions, all right? And they get created by higher level modules, like this top module here. Now, some of the tabs looking wonky right now. I apologize for that. We'll have to clean that up. But bottom line is, the top module is a very widely used convention. It's purely a convention. It doesn't mean anything. But everyone follows it, so I'm going to as well, and it's really convenient. This is like the main in a Java or C, C#, Python, whatever, your main entry point of the whole thing. That's your top level piece of hardware. And inside here, we can create things. This is how I create a counter, and I connect it into my circuit. This is me creating something that controls one of the pins in the FPGA. And it becomes part of the circuit as well. So we'll talk about all this stuff as we go along, but from the beginning, here's a blinky program, and here's a way to run it, all right? There's a simpler one over here. Well, actually, that one's too simple. Blinky number 1 over here, he only has a top. Oops. Habit, I suppose. So this one has a single module. It does not create any other modules. By definition, it's simpler. You don't see the pin configuration data in here either. This one is a little bit more simplistic in that we use the defaults for a number of things. So the reason I gave you these files, the minimal, as we go back simpler and simpler and simpler, is simpler still. This one has a button and an LED. And this way this program works is when you press the button, the LED goes on. When you release the button, the LED goes off. I would have started with this, but neither the Icestick nor the UPduino has a button on it, which is really annoying. So I'm going to have to solder the headers on my UPduino or something like that, put in a breadboard, hook up some button, put some wires in there, blah, 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 blah. You want to try that on your own, knock yourself out. Start with this, okay? If you cannot turn the light on and off with a button, you do not want to go forward and make more complicated things, okay? So you've got minimal, which just turns the LED on when you press the button. And you'll notice because it doesn't have a clock or anything, it doesn't count, it doesn't have any stateful information, you don't even need to worry about the oscillator that's not hooked up on the UPduino. All right, that one is as simple as it gets. Then you can move on to blinky. And this one needs the clock. You need to have that hooked up. And it will flash these LEDs on and off as it goes, as the clock ticks, okay? And we'll talk about how this works and why and how you use it and what it means some other time. But that's what's going on in this particular app, okay? And you already saw Blinky 2 as well. Take another look, one final passing look at this guy. And he's got even more stuff going on and submodules and things like that. This gets more complicated, okay? So we got plenty to think about, plenty to do, and if you want to work ahead, knock yourself out. Plenty of documentation floating around on the internet. There's probably a whole bunch of other tutorials that go about this in very different ways. I don't like to just parrot the same thing that somebody else did. If you think something's better, let me know. If I left something out, let me know. We can evolve this to suit our needs as we go. All right? So, thanks for watching. I'll see you next time.